We are going to study density metrics with periodic boundary conditions today. We already learned uh, about the density matrices with the periodic boundary conditions. However, we try to expand our knowledge in this area. First, we will go through some details we already learned, since this is a revision also. And also, we are going to learn several new things. So we defined a density matrix using this expression. Rho of x, x prime, and beta is equal to sum of psi n of x times exponential of minus beta en times psi n star x prime. So the psi n is the eigenfunctions or the wave functions of the particles. En is the energy of the nth energy state, and psi n means the eigenfunction of the nth energy state, and x prime are two different locations of the particle. So when x is equal to x prime, which are in red in this matrix, are the diagonal terms, and the other terms in green are the off-diagonal terms. And here this exponential of minus beta en is proportional to the probability of occupying the quantum state at a given temperature. So this is the this exponential function is proportional to the probability of occupying the nth state at a given temperature. So we know that beta is equal to 1 over kBT. Kb is the Boltzmann constant, and T is the temperature. All right. So let's look at the Schrodinger equation. So here, Schrodinger equation has this Hamiltonian operator, which has two parts: kinetic energy part and the potential energy part. So kinetic operator is given by minus h cross squared over 2m times double squared over double x squared, and the potential operator is denoted by v. So that operator, Hamiltonian operator, times the wave function gives us the energy times the wave function. So this is here the Hamiltonian is actually a matrix. We can write it in a matrix form. So this is an eigen value problem. So operate matrix times eigenvector is equal to energy, the eigenvalue times the wave function or the energy eigenfunction. And for free particle, we know that the potential must be equal to 0. So we substitute 0 for v here. So we are getting the Schrodinger equation as kinetic operator times the eigenfunction is equal to energy times the eigenfunction. And to make it more simple or make it more convenient, I'm assuming that h cross is equal to 1 and m is equal to 1. So this expression becomes minus 1/2 double squared psi over double x squared is equal to e times psi. So this is the Schrodinger equation we got now, and here we are considering a one-dimensional problem. So we have only one direction, x, and we consider that a box with length L with periodic boundary conditions. So if the length is L, we can write that psi of x is equal to psi of x plus L. Then if we and also it should satisfy psi of 0 is equal to psi of L. That means the wave function's values at 0, x is equal to 0 and x is equal to L must be equal. And also the first derivative of the wave function at 0 and L are also equal to each other. So if you consider the above expressions or the formulas, then these two formulas, we can identify that this expression satisfy the both two expressions, expression 1 and expression 2. So it is psi of x is equal to a times exponential of I kx. Here I is the square root of minus 1. And k is a constant and x is the distance. So let's plug this expression at this let's plug this expression at this formula. So then we get a is equal to a times exponential of ikl. Then that means 1 is equal to exponential of ikn. Then it gives us kl is equal to 2 pi n. It is because exponential of I to 2 pi n, this is equal to 1. So remember that n are actually like 1, 2, 3, and so on. These are actually integer values. So so based on this, we can rewrite the wave function as psi of x equal to a times exponential of I times 2 pi over L times x, because k is equal to 2 pi n over L. Yeah, so here we have to have n. So 2 pi n over L is written instead of k here. And then we are normalizing this. We are normalizing this expression. If we are normalizing this expression based on this formula, we are having that a is equal to 1 over square root of L. So we found a in terms of L, and we can we can substitute a in this expression and rewrite the wave function in this form. So sine of x is equal to 1 over square root of L times exponential of I times 2 pi n over L times x. So next, what we are going to do is we are going to find the energy, find an expression for energy. So we know the Schrodinger equation with the potential, with the zero potential. And we can write in this way. And we also know the wave function. So I put it here, and I differentiate this. I calculate the second derivative with respect to x, and I'm getting this expression, and this one, this expression, this one is psi, and we have this factor, and if you do the math, you will find that En is equal to 2n squared pi squared over L squared, because psi goes away with this one, this side over at the right hand side. So we are having the expression for energy for nth energy state. Okay, so we have this expression for a particle in a box with a distance L, particle in a box with a distance L. Remember that in a particle in a box, we consider that V is equal to 0. However, the energy may be potential energy may be infinite at the boundaries, and here 0 and here n. So this is the density matrix expression. So we can substitute this exponential functions. We can substitute the wave functions in this density matrix using these exponential functions, and also we can substitute En with using this expression, and what we get is this. So rho of x prime beta is equal to 1 over L sum over n for exponential of minus beta to n squared pi squared over L squared times exponential of I2 pi n times x prime minus x over n. So for two locations called x and x prime, and for given temperature, this is the expression for density matrix. So we are trying to modify the density matrix expression. Here we consider that consider some small change in n, small change in n, and remember that as I told you before, n is like 1, 2, 3, like that. These are integer values, so the successive smallest n, delta n, or smallest n difference is coming from is 1. So because difference between two successive n values is delta n is equal to 1. So I can easily put the delta n over here without disturbing this expression, without doing any big change to this expression. I can just plug this delta n over here. So we are getting this formula, and then we know that k is equal to 2 pi n over L. We could show that previously. So to go back, we learned it here, right? So we can write k is equal to 2 pi n over L. For a small change in delta n, we can say there's small change in delta k. And we know L is a constant for given box. So delta n is equal to delta k L over 2 pi. So I plug this here, and I'm getting this expression. This L goes away because of this 1 over L factor, and instead of 1 over L, we are having 2 pi now, and we have delta k in this expression. Yeah. So we wrote the expression of a density matrix for particle in a box with respect to delta k. So now for a free particle, actually L must go to infinity. That means the particle, if a particle is actually free, then it has to have a huge space without any potential. So L goes to infinity for free particle. So when L goes to infinity, delta k becomes very small, because delta k is inversely proportional to L based on this. So when L goes to infinity, that means delta k goes to 0. Delta k goes to 0. So therefore, this becomes a continuous problem rather than a discrete problem. Here it is a discrete problem, but if delta k goes to 0, it becomes an continuous problem. So rather than writing this as a summation, we can rewrite this in the integral form. So we are integrating this from negative infinity to positive infinity with respect to dk. So we integrate this, and we are having this formula for free particle. It is density of a free particle is given by this expression. It's the square root of m over 2 pi x squared beta times exponential of minus n times x minus x prime squared over 2 h cross squared times beta. So we rewrote the h prime and we re-added the h prime and m to this expression. We previously considered that h cross and m both are equal to 1, but we are not considering it any longer in this expression. We reconsider those values here. All right, so we determine the Bayesian matrix for a particle in a box, and also we can consider a particle in a box with periodic boundary conditions. So we already found the expression for the density matrix for particle in a box with the periodic boundary conditions. Now, so basically, this is also periodic boundary. This is also based on the periodic boundary condition. Now, what we are going to do here is in this summation we considered the we considered the we considered this summation. We calculated the summation over the n values from minus infinity to infinity to positive infinity. Now, however, we are now going to rewrite this expression based on the Weinstein numbers. So let's say what that is. So this equation gives you the Poisson's sum. So based on that, when n is equal to minus infinity to infinity, when we calculate the sum of some function of n from n is equal to minus infinity to infinity, we can write it as sum over omega from minus infinity to infinity time over summation over omega from minus infinity to infinity for this integral. So in this integral, we are integrated from minus infinity to infinity with respect to this parameter phi, and g becomes a function of phi, and there's a factor exponential of I times 2 pi omega phi. So we can this is the Poisson's sum formula. So, and we can convert an infinite sum to this based on this transformation. We can rewrite the infinite sum, and therefore we consider this summation, and instead of n values, we can instead of using n values, we are going to use omega values to calculate the sum. So we are rewriting the expression. So this omega parameter is called the Weinstein number, and here in this exponential factor has omega L as well. We have now omega L as well because of this term. So this because of this exponential term. So so we rewrote the density matrix based on the winding number. Okay, so let's consider this integral within this summation. We have this integral. So we are going to solve it. So if we integrate this, we are having this solution is equal to L times square root of 1/2 pi beta times exponential of minus x minus x prime minus omega L squared over 2 beta. And then we can substitute this integral with this solution, and we are having a more simplified version of density matrix expression in terms of the winding number omega. And then here we know the free particles density matrix expression, and you can see that within this summation, only the difference is there is a it doesn't have this omega L term. So this is like so this is like rho free x exponential plus omega L and beta. So we can indicate this in this form. Then we can rewrite the expression of density matrix for particles in a box in terms of this density matrix of a free particle in this way. So in a periodic boundary based on the periodic boundary conditions, if a particle exits one end, it enters at the other end. So that means so if this is the if this is omega equal to 0 case box, then if a particle is over here, and if it comes somewhere here, that means it appears over here. Let's say the distance over is d, then this distance is d. So we can use these winding numbers to understand how many times it is winding around this period within this unit cell. So it's like one time, second time, third time, likewise. It winding around the particle, winding around the box. Okay, and then also we need to know that omega is equal to 1 means it shift by 1 box length, right? That means it shift to the for the next box. If it is -1, then it goes to this box. If it is +2, that means it goes to the next box. -2 means it goes here. But wherever it goes, it comes back to the same box based on the periodic boundary conditions. So omega can have positive and negative values, positive and negative integer values. If omega is equal to 0, that means it moves within this box. Okay, now we have the density matrix expression for based on with respect to the omega, and in this expression we have x and x minus x prime, and within the exponential term. And if you consider the in this matrix, matrix, as I told you before, these diagonal terms are diagonal when it is a diagonal term, x is equal to x prime, and when x is equal to x prime, this goes away. Therefore, only omega L term survives within the exponential function. And we know that if we can calculate the partial function by integrating the diagonal terms. So we are integrating it with respect to x, and so it is easy to integrate this with respect to x, because there is no x value, x variable within this summation. So we have this integral, and it gives us L minus 0. That means L. Therefore, finally, we can write or we can mention the partial function as L times square root of m over 2 pi h plus squared times beta times summation or sum of exponential of minus omega L squared over 2 beta over minus infinity to infinity. So we derived the expression for free particle or flat particle within a box, periodic box, expression for particle in a periodic box for partial function, and now we have two ways of writing it. Here we found the partial function. We found the expression for partial function in terms of n, a quantum number, and here we have the same thing as a function of omega, of the binding number. So we learned how to find the partial function, and also the density matrix terms in terms of omega or the Winding number. So that's all for this lecture, and hope you understood what we learned about the density matrices and how to derive the expressions for partial function and also the density matrix in terms of the quantum number n and also the Winding number. Thank you.